Now we are going to demonstrate the software is EMQ. Uh, Academical lab solution is dealing with the software EMQ in India region. EMQ stands for Engineering Modeling Collaborative Userware and Benchmarking Environment. This is the electromagnetic based software which will offers various kinds of platforms. Generally, in the electromagnetic side, mainly we are going to simulate various kinds of wideband antenna, the metamaterial structures, complex material media structures, circuit simulation. These all could be taken care by the EMQ. The EMQ basically categorized into these sections. There's six sections are present in the EMQ. One is the CubeCAD. CubeCAD is basically the CAD foundation models are there. Small models are there where you can build your structures basically, and you can import the 3D objects. You can export the 3D objects also. This is the first model called as an EM tempo, which is based on the finite difference time domain method, which is a full wave method, and that EM simulator is basically for transient and wideband modeling of 3D structure, circuit, antenna, metamaterial, and various complex material. Even a mobile with the human being kind of calculations also you can do by using FDTD. This is the EM Terreno, which is again a very special model which only the EM cube is going to be support, because mainly the peoples are conscious about the propagation modeling within the within your urban area, within your buildings or any complex area. So these times the Terrano will help you a lot. This is a physical based UTD, uniform theory diffraction and physical optics based model. In this you can model a total radio propagation in urban nature and indoor environment. So you can build your colony, you can put your BTS, and you can simulate the entire colony with the electromagnetic pattern. So this is the EM Terrano. Then the EM Picasso is there, that is more popular in the side of the planar circuits, where methods of moment is full wave technique. It is utilized in Picasso, and the structure is modeling for printed all types of printed antennas, microwave circuits, periodic planar structures, filters, couplers, resonators, all kind of planar microstrip structures. It is suitable. We can easily develop in EM Picasso. EM Libra is especially MOM 3D models which will solve the problems. Again, it is also full wave methods, and for wire antenna it is mostly useful. Various kind of log periodic antenna, Yagi-Uda antennas, these all antennas kind of wire antenna you can cover in Libra. In fact, EM Tempo also take cares about this antenna, because FDTD is very robust method, so you can also cover these things. EM Lumina is only the special models related with the Huygens surface, RCS, radar cross-sectional area, large platform interactions, like a ship, like aircraft, and these things also you can take care. So this is the total package. In this package we are covering antenna design, simulation, metamaterial structures, complex materials, as well as the wave propagation side, which is very big, like colony and BTS side, the planar circuit, microstrips, and these things. And all types of antennas is covered in the Libra, and the bigger structures and large structures like helicopters, along with antenna simulation, or the ship along with antenna simulation, this is covered in the EM Illumina. So CubeCAD is a special structures which will in the package of giving the support for all this package. So now I demonstrate a simple example of a wire antenna by using FDTD method. So for the FDTD, you can see this three windows are there. This is the window called as a schematic window. This window is called as a project browser. This is called as a general toolbar. General toolbar having the various kinds of CAD primitives files, like a box is there, cylindrical is there, cone is there, pyramidal is there, circle is there, and these all boxes are there. Here you can utilize this CAD primitives file to construct your signals. These are the lines where grouping, adjoining, other features are there. Here you can join the two groups. Here you can subtract the things, union the things, extract the things. So these are the different models which requires. Even this is the for the measurement, distance measurement, for the arc measurement, angle measurement. So these are the points where you can do this thing. Even the filling kind of structures are available. Then a strip sweep, then bridges, then this symbol is for the skin stitching. So these are the various CAD primitives files are available in this. Even you can see this is in the four structures, or if you go on, you can place it in one. In this is the various views are there, perspective views. Okay, so we start from our antenna. Suppose I want to design an antenna on 1 gigahertz. First I have to set this is the millimeter wave. This is the here the unit we are going to set for the grid spacing, that is 5 mm. By default it is frequency, suppose 1 gigahertz, or you can change this frequency 2.4 gigahertz, or you can place anything like but you have to place in 900 megahertz also, but okay, we keep it at 1 gigahertz only. So you can change also the bandwidth of this frequency. Click on OK. So first is the millimeter setting, this second is a frequency setting. After that you have to select EM tempo. So click on EM tempo. When you click on EM tempo, there's a large tree structure is comes across you. This is actually our project browser. The project browsers means you have to it is like our same like our form, like exam form, like we have to fill from the start and slowly go up to end. So one by one column we are going to feed, and that will excite our antenna. Suppose I want to design an antenna which runs on 1 gigahertz. So first I have to calculate the wavelength of our antenna of 1 gigahertz, 1000 megahertz. So 0.3 meter is my wavelength. So into if I place 1000, so 300 mm is the wavelength. So divided by 2 is 150. 150 mm is the length I require for the dipole antenna. So I go to dipole, I take a dipole, I put it in straight manner. Okay, now this dipole, so I have to write name dipole. Okay, so here always keep, if your things are vertical, then you just place always -180 and -90, and if you place it, this is a straight line. Okay, and you have to place 150, so that is the lambda by 2 distance of the wavelength. So keep it okay. So just see. Okay, now this blue box you are seeing, that is the FDTD box, boundary box is there. So this boundary box is coming due to this setting. This is already automatic settings are done, so no need to edit even the settings. So our first dipole drawing is over, so we have to close this dipole drawing. So this is a different materials are there. PEC means perfect electric conductor material, perfect magnetic conductor material, dielectric material, anisotropic material, dispersive material. So these are the different materials which is generally utilized in various complex environment, like metamaterial, FHS, FS, SS, frequency selective surfaces. So this is now second thing automatically done by the computer, third thing also automatically done by computer. Now I have to give the lump source. So in the source means this is the excitation method of antenna. Either lump source, ideal source, lumped load, waveguide source, plane wave source, Gaussian beam. These are the different source are there. In the lump source, you have to just go and say insert. When you just insert it, dipole and plus z direction 75. So here you can see exactly means our total length is 150 and half of the length is 75. Amplitude is 1, phase is 0, resistance is 50 ohms, and click OK. So if you click OK, this is the port is selected. Now your port is also over. So only the last is observation. What observation you want to make from this? Definitely a far field I want to observe. So click on the right click on this, say insert parameter, insert radiation pattern. So in the radiation pattern, moreover these windows are disabled. Increment is 5 degree. Non-principal plane. You can change the plane. You can change the background. But keep this suggestion is to keep this all things as same. You can add the directive gain. I want to calculate half power beam width also, so this will directly tell you the half power beam width, front to back ratio, axle ratio, maximum side lobe ratio, all this ratio. Okay, and say okay. So if you click OK, again a small boxes comes here, that is again a boundary condition box which will take care about your far field pattern. So this again a field sensor is there. You can also insert a field sensor. Now when you say insert a field sensor, means this is a square coming, means you want to observe like this z direction or y direction. Y direction means you can see this vertical block is coming. Okay, so in the y direction if you want to see, just click OK. So this sensor coming. Last is the port definition. Go to insert port definition, click on this and say OK. Just so this is the actually observation what we have to make. So we have to close it. Now we almost done the physical structure. Computational domain is automatically, discretization is automatically. Only we have to give source and observation and draw the picture. So this is the very convenient way to draw the things. Now we go and say simulate. Simulate, when we say simulate, so there are different types of analysis is there. Frequency sweep analysis means you put a start frequency and stop frequency and simulate the antenna. Otherwise the parametric sweep means a particular parameter you vary and sweep the antenna. Angular sweep is there, RT macro model, dispersion sweep, Huygens sweep, optimization, SDM. So apart from that, analysis is sufficient. Say, and even you can change the FDTD settings also. These are the FDTD settings. Put the convergence on the both. Use the multi-core core CPU solver. Say run. Yes. Now it is running. This is actually convergence happens on your frequency. Okay. Now go to again observation. In observation, we declare already far field. The far field, you can see this is the theta, phi, total. So these are the radiation patterns of the dipole. Even you can look from various angles. This is the top view, radiation pattern side view. This. So this is the view, and you can go on those like. So these are the top, side, different views are there. Okay, so we close it here. We go to field sensor. E total. Okay. Okay, now go to E total properties. Make it dB. Okay. Now you can see this is the actually at the width side the radiation is higher. In the middle side radiation is lower. This is the box where you can see the legend where the type is E magnitude total and maximum power is 37.8 dB volt per meter, and that power we are observed in this side because here is always the edges are responsible for the field generation, and here the fringing field is present. That's why on the dipole this side and this side the fringing field is present, and in the middle side the power is less. So this is the E max total, this is the H field. Exactly opposite, here is the lesser energy, in middle is a higher energy. So E and H is exactly opposite. Even the E is a higher at the energy here, lower the here, but EH mag, yeah, already lower here. Even you can see the HX E magnitude in the X direction, how it is propagating, how it is the gradient is there. E phase there, E magnitude at Y direction, and you can see on the exactly on the dipole what is going to be happen over here. Then there is an E magnitude at Z direction, Z direction, obviously the Z direction is responsible by their dipole. So only the dipole edges are going to be responsible. So this is the actually our pattern of this thing. Now we demonstrate a 2D pattern. In the 2D pattern you can see this is again the box. This box you have to select directivity. Suppose if you want to see the directivity, go and view 1.66 dB directivity is there. If you want to see the HPBW, half power beamwidth or front to back ratio, you just bigger it one like this one. Directivity gain, I want to see the half power beamwidth in YZ direction and say we want 75 degree is the half power beamwidth. If you want to see the plots, then you just click the see the Cartesian plot or polar plot. If you want, you can go to polar plot YZ direction and say plot. Now you can see the 8 of the pattern of the dipole. Okay, so here is the dipole patterns are coming, and okay, so this is the different pattern in the same. You can also observe in the Cartesian plot also. So there is a Cartesian plot. Here is the null degree. Here is the pattern post side and broad side. At the both side you can easily observe over here the angle versus E field strength. Also you can observe the VSWR. If you go with the VSWR, this is the VSWR they are writing like this here. So this is the total VSWR they are writing. Okay, and if you want to see the plot, then just click on VSWR plot and say plot. So this is the VSWR plot you are getting observed over here. Okay. So you can place the marker also here and see the VSWR at particular point. Here is the VSWR is very small, 1.6 VSWR you are achieving at 868 megahertz, and here is the band, actually the band of occurrence is there. So this is actually the related with the plot. Even you can see the 3D plot, input output files, text file, image file. These all files you can import this file. You can see in the notepad. You can plot this file. These other facilities are present over here. In the next video, we are going to see about array, how to make the array in the FDTD. Thank you.